Okay, today's tutorial is on using the VI-VF DAT or VIF-DAT method for solving kinematics problems. So far we've already come up with this equation sheet where we have 5 kinematics equations and what we call the unused variable. So now I'm going to work a couple example problems to show how we select the correct equation to solve the problem. You can find these problems on page 27 of the class notes that I've given you. So let's start with this first problem. All of our problems we start out with writing VI, VF, DAT. Right? So that's where we come up with the VIF-DAT. Right? So we start with this guy, and we have a student on a bicycle starting from rest. All right? So that is a piece of information, starting from rest. What that means is starting, that's the first thing that happens, so that's telling us that VI is equal to 0. So we can put 0 in right there. Right? So the student starting at rest has a constant acceleration of 3 meters per second. So constant 3.0. On some of the quest assignments, you might see where they talk about an average acceleration. Well, they mean the same thing. Well, all we do in this class is what we call constant acceleration. So average acceleration would be the same thing in that context. Alright, so that's all the information we have out of there. So now we got to start working these problems, A, B, C, and D. So if we look, A says after 4 seconds. So after 4 seconds is time. How far have they gone? How far would be displacement in this case? Question mark. And then we have this guy that has nothing to do with the problem. It's very key to identify this variable that has nothing to do with the problem, because when we go back to our equation sheet, that's what we call the unused variable. So the unused variable in this case is VF, so that helps us identify this is the equation that can be used to solve that problem. So let's take a look at that. So next we write our equation. Displacement equals VIT plus 1/2 AT squared. Alright, now we started from rest. So that means this equation, this term right here can go to 0. So I don't have to plug in 0 or anything like that for this equation, because, or this part of the equation, because I already know it's going to 0. So I just denote it that way. So my next line, I substitute my numbers. So I get 1/2 A, which is 3, T squared, so it's 4 squared. Now be careful. One common mistake I've seen throughout the years, our students try to square the A times T. It's just the T that's squared, just the time. Alright, so that's going to give us displacement equals, well, this part is 1/2. This is 16, so 1/2 times 16 is going to be 24 meters. And that's our final answer. Alright. Second problem. We're still using all the same data, but this time we're saying, hey, how fast are they going? So how fast would be velocity final? One thing I like to do is maybe separate the problem out and say, okay, now we're at part B. So we still start from rest. Now this is the question mark. This is 24 because we just solved it. This is 3. And this is 4. Alright. So the cool thing here is now we have 1, 2, 3, 4 numbers and a question mark. What that means is we can use any equation that will solve the problem. So the equation we're going to use is equation number 1. Number 1 is oftentimes the easiest one to use right there. Alright. So equation number 1. velocity final equals velocity initial plus AT. Again, velocity initial is 0. So we can go velocity final is A times T. A was 3, T is 4. 12 meters per second. Part C. What is the average velocity during the first 4 seconds? So we're still talking about the same time frame, but now we want average velocity. Alright. If we go to this equation sheet, we don't really have an equation for average velocity. But this is average velocity, which is this part of this equation. So when we have constant acceleration, we can just average the initial and the final and get the average velocity. So V average is equal to VI plus VF over 2, which is VI is 0 plus VF is 12 over 2 is 6 meters per second. Okay? Now, last, let's look at this part. This part asks, how far have they gone by the time the velocity is 20 meters per second? Well, if we look at 4 meters per second, alright, we've gone 24 meters. And we have a velocity of 12 meters per second. So this time data and displacement data no longer works because we have a different location that we're looking at. We're looking at how far it's gone once it's gone to 20 meters per second, which is farther or faster than at 4 seconds where it's only 12 meters per second. So we have to start the problem over, but we can use some of the same information. It's still starting from rest, but now we're looking at when it's going 20 meters per second, and we still have an acceleration of 3. This time we're looking for how far, and we don't know how long it took. So if we look at that, time is our unused variable, so there's our equation. Velocity final squared equals velocity initial squared plus 2AD. Velocity initial is 0. So velocity final is 20 squared equals 2 times 3 times D. So I'm going to solve the rest of this. So I'm going to move these around. So I have 6D equals 20 squared, which is 400. D equals 400 divided by 6, which equals 67 meters. Okay, so there's the first example. Next, let's look at problem number 2. So for problem number 2, we have the following. So a car is moving down the road with a velocity of 20 meters per second. That looks like it's probably the initial velocity, but let's continue reading to make sure. When the driver decides to speed up, alright, it takes the car 167 meters to reach 30 meters per second. Okay, so later in time we're going faster, so that one's velocity final, and this is indeed velocity initial. So we have velocity initial of 20, velocity of final of 30, and it took 167 meters to do that. Now let's look for a question. What is the acceleration of the car? So acceleration is our question, and time has nothing to do with the problem. So if we go back down our equation sheet, we find time, nothing to do with the problem, that's the unused variable. We use equation number 5. So equation 5, velocity final squared equals velocity initial squared plus 2AD. So let's put in our numbers. Velocity final is 30 squared equals 20 squared plus 2. I'm going to write D in here, which is 167, and then A. So I just moved the variables around to put those two together. Now let's do the math. 900 equals 400 plus 334A. So then we end up with 334A. I subtract 400 from both sides. I'm left with equals 500. So the acceleration is going to be 500 divided by 334, which gives me, I rounded off to 1.5 meters per second, which we can just write as meters per second squared. Alright, next part of the question is how long did it take? How long is time? Alright, so back to this, we have all of our variables now except time, so we can use any equation that makes it easy on us. Alright, the equation that makes it easy for us is equation number 1. Whoop, equation 1, right there. So equation 1, velocity final equals velocity initial plus AT. Final is 30 meters per second, initial is 20 meters per second, plus A, which we just calculated as 1.5 T, 1.5, whoopsies, so 1.5 T equals 30 minus 20, which is 10, so T equals 10 divided by 1.5, which is 6.67 seconds. Okay? So now that we've done a couple example problems, your task is to work on this. Alright. So how do we do these problems? Well, we look. We're given T, VI, VF, and we want to find A. So A is the question mark. What's not used? D. Alright, so when D is not used, that's equation number 1. Alright, and now we can solve it. So using equation 1, we know that VF equals VI plus AT. So we have 14 equals 2 plus 6A. That's going to give us 12. So 6A equals 12. A is going to be 2 meters per second squared. Okay, and we see down at the bottom here, the answer for number 1 is 2 meters per second squared.